Let's look at the fundamental theorem of calculus part 2. It states if f is continuous on the closed interval from a to b, then the integral from a to b of f of x dx equals capital F of b minus capital F of a, where capital F is any antiderivative of the function. That is, the function such that the derivative of capital F equals f. Let's go ahead and look at the proof. Let's start with g of x equals the integral from a to x of f of t dt. We know from the fundamental theorem of calculus part 1 that if we took a derivative here, we would get f of x. So that is g is an antiderivative of f. So if f is any other antiderivative of f on the closed interval from a to b, then we know that capital F and g must differ just by a constant because they are both antiderivatives. So we know that capital F of x would equal g of x plus c. Now let's go ahead and look at capital F of b, so that would be g of b plus c, and capital F of a, which would be g of a plus c. And let's go ahead and subtract these two equations. That would leave us f of b minus f of a equals, subtracting these two, g of b plus c minus g of a plus c. And we can see that these would cancel, and that would leave us with g of b minus g of a. But wait a minute, what is g of a? If we look up here, g of a would be the integral from a to a of f of t dt, so we know that that's 0. So that's gone, and we would have g of b. So what is g of b? If we look up here, it is going to be the integral from a to b of f of t dt. So we started with this, and we ended up with this. So this will equal f of b minus f of a, where this capital F function is any antiderivative of little f. So with this, let's just kind of look at some notation. So we have our limits of integration. Remember, this is called our integrand, and this would be x as our variable of integration. So capital F is an antiderivative of little f, and we're evaluating it here at b minus evaluating it at a. And our shorthand notation is we write the antiderivative, we can make a line and put our limits here, and this means we need to evaluate it from a to b. In other words, we need to do this. So let's look at an example. So this definite integral is going to equal, first I need to figure out the antiderivative. So what function's derivative is cosine x? Well, that would be sine x. And then we make our notation. We need to evaluate that from 0 to pi. So by the fundamental theorem part 2, that means the sine of pi minus the sine of 0, because I'm taking the antiderivative at b minus the antiderivative at a. And of course the sine of pi is 0, and so is the sine of 0, so it looks like our answer here is 0. Now let's see why that might be the case, that the answer would be 0. Well, if we looked at the graph of cosine from 0 to pi, cosine of 0 is 1, and the cosine of pi halves is 0, and the cosine of pi is -1. And so our curve would go like this, and we computed the definite integral, so we would have the area above the curve, and this would give us a plus, and this area below the curve would have a minus on there, and they would cancel out, and indeed we would get 0 for net area. Looking at another, we have the integral from 0 to 1/2 of 1 over square root of 1 minus x squared dx. So let's go ahead and think of what is this the derivative of. So I'm looking for an antiderivative, and oh, I recognize that as inverse sine. So it needs to be evaluated from 0 to 1/2. So now we'll evaluate that. That's going to be the inverse sine of 1/2 minus, cut it down below, inverse sine of 0. The inverse sine of 1/2, so I'm wanting the angle whose sine is 1/2. So that's going to be pi over 6 minus the angle whose sine is 0, and that's going to be 0. So it looks like our solution is pi over 6. And let's look at one more example. We've got the integral from 1 to 4 of the quantity 3/2 squared of x minus 2 over x dx. So what we want to do is figure out an antiderivative. I'm going to put it up here a little higher and small so we can fit this in. And so I'm going to think of this as 3/2 x to the 1/2. So what was the function when I did its derivative? I got 3/2 x to the 1/2, and I can see that would be x to the 3/2 with the power rule applied, because if I took a derivative of this, I'd move power out in front and decrease the power by 1, and it would look just like that. I'm just going to do minus, because we know when we integrate we can do term by term and then combine them. What function's derivative is 2 over x? Well, that's also 2 times 1 over x, so I can put the constant out in front, and what's function's derivative is 1 over x. Well, that's going to be the natural log of x. So then I need to evaluate this from 1 to 4. F of b would be 4. Converting this to radical form so we could think about working it, this means the square root, and this means the power of 3 minus 2 times the natural log of 4. So that's the f of b part, and then we need to subtract f of a, so that's going to be subtract 1, and if I did 1 to square root and cubed is still 1, minus 2 times the natural log of 1. Let's see what we can do to simplify this. So we can square root the 4 and get 2 cubed is 8, minus 2 natural log of 4, that won't simplify, minus 1. Now this minus applies here and makes it a plus, but the natural log of 1 is 0, so that's gone. So it looks like our final answer to this will be 7 minus 2 times the natural log of 4. And we should leave answers in exact form unless told to do otherwise. I wanted to make one more comment. This is correct. Maybe you looked at the back of some book for this answer to this and you saw 7 minus the natural log of 16. I'll have students come ask me questions like, I think I got it right, but the answer says it's this. So what if it says it's 7 minus the natural log of 16? Well, remember our log properties, the third property of logs, and this is kind of in the reverse of how, a lot of times how we use it. If we have something multiplied in front, we can put it as a power. And so this is equivalent to 7 minus the natural log of 16. They are both correct equivalent answers. What's wrong with this calculation? We have the integral from -1 to 3 of 1 over x squared dx. Well, if I looked at 1 over x squared, I could express that as x to the -2. If I'm thinking of an antiderivative, it would have been 1 higher power, and then we divide by this. And oh, that's exactly what I have here, evaluated from -1 to 3. So this would be -1 over x evaluated from -1 to 3. So putting in the 3, the -1 over 3, and then subtracting. Putting in the -1 would make those a positive, but then we subtract because we're doing f of b minus f of a, and then combining those I get -4/3. So what's wrong with this? That is not the correct answer. Why not? Because the fundamental theorem of calculus has the requirement that f be continuous on the closed interval from a to b. And when we have this function, it has a discontinuity at x equals 0, and I'm trying to integrate and include that point of discontinuity. So f is not continuous from -1 to 3, and therefore the fundamental theorem does not apply. What you get is not a valid result. The main thing we want to be careful about is we don't try and apply the fundamental theorem if we have not met the conditions of the theorem. Let's just summarize then the fundamental theorem of calculus, putting the two parts together. Suppose f is continuous on the closed interval from a to b. Part 1, if g of x equals the integral from a to x f of t dt, then the derivative of g of x equals f of x. And part 2, if we have the integral from a to b of f of x dx, then that equals capital F of b minus capital F of a, where capital F is any antiderivative of the function. So anything where the derivative of capital F equals f. So derivative of the integral, when we meet the conditions, undo each other. And if we want to do a definite integral, we don't need to actually calculate the area and sum things up like we were doing. We can find the antiderivative and take f of b minus f of a. What this tells us is an important fact that differentiation and integration are inverse processes. So we need to make sure we know the difference between a definite integral and an indefinite integral. A definite integral has limits of integration, and if our limits of integration are constants, now it's possible they could be functions, but if they are constants, when we compute this, we find the antiderivative, and then using the fundamental theorem of calculus, we evaluate this at capital F of b minus capital F of a. So we get a number. We're done. The answer is 3 or 5/2 or something like that. An indefinite integral, we have no limits of integration, and when we are done, we get antiderivative of f of x plus a constant of integration. So we will get a function back, not a number.